Okay, let me welcome you to this lecture 7 of our course on topics in reinforcement learning. And today we're going to look at some extensions of the rollout algorithm. And then next week we're going to go into neural networks. This is our last lecture on rollout for some time. So we're going to go back to deterministic problems and discuss a constrained version of rollout, a more general version of rollout where there are some additional constraints. And then we're going to specialize this particular type of rollout into a broad class of discrete optimization problems, including combinatorial problems that are very much at the forefront of optimization today and have been for a long time. Then we're going to look at a different type of problem where instead of minimizing the expected value of the cost function, we minimize against the worst possible choice of an adversary. This leads to Minimax Control and game theory, and we're going to discuss how rollout can be used within that context, as well as more generally, approximation in policy space, in value space. So let's start with constrained rollout. And I'm going to begin with an example that you know and love. This is our 4-city traveling salesman problem that involves travel costs, which are shown here. The numbers are, I think, pretty much the numbers we have been using. We have been trying to obtain the unconstrained minimum cost tour. A tour is a trajectory from A through the cities and back to A. And the unconstrained minimum cost tour is this one here. Now, suppose that there are some constraints here. In particular, there's a safety constraint that we have to obey. And each tour has a safety index or cost associated with it, which is numerical. And we require that we're required to find the minimum cost tour out of those tours that satisfy this constraint, where the safety index is less than 10. So this will disqualify this tour, which happens to be the optimal. It will disqualify another tour, this one here, and the other tours are allowed, okay? So out of those that are allowed, we want to find the best one. So how do we deal now with this extension of the problem? Okay, so let's review the unconstrained rollout algorithm and see at what point we have to modify to deal with constraints. Remember that the algorithm constructs a sequence of trajectories. In the case of the traveling salesman problem, trajectory is a tour, starts from the initial state and ends at the final state through a sequence of controlled selections. And the rollout algorithm constructs a sequence of trajectories, one at each of n steps. And these trajectories under a sequential improvement condition have a monotonically non-increasing cost. And that's really the core of the theory, that in this way we are able to look at trajectories that go from beginning to end, have vision, but also decrease the cost as we go along. In particular, we decrease the cost if we start from x0 and use a heuristic. Now, at any stage k, the trajectories from k onward, they share the same initial portion. In other words, at time k, we have already selected k controls, and we have gotten from the initial state to this state x tilde k. And now we look at all possible next controls, and we run the base heuristic to generate candidate trajectories, which correspond to the different controls that you can apply. So at x tilde k, we have this trajectory, tk, which is the cost, which involves this initial portion plus the remainder that's completed with the base heuristic. And then we construct candidate trajectories that go up to xk the same way, and then we get a choice of uk, and then we run the base heuristic, and we find the candidate trajectory that has minimum cost, okay? Out of all those here, it's the one that has minimum cost. First stage cost plus the cost of the base heuristic. And under the sequential improvement condition, we have that each time the new trajectory is no worse than the preceding one. In particular, the last one, the one obtained by rollout, is no worse than the initial trajectory, which is the trajectory generated by the base heuristic. So now, as we generate these candidate trajectories, when we have constraints, some of these candidate trajectories may not satisfy the constraint. So the remedy is very simple and fairly obvious. In order to deal with the trajectory constraint, we discard all the candidate trajectories that violate the constraint, and we choose tk plus 1 to be the trajectory that is best out of the ones that satisfy the constraint. It's very simple. We get a number of trajectories. Some of them violate the constraint. We throw away the ones that do and do the best we can with the others. And we still maintain, obviously, this property here, as long as we can always find at any xk that we generate, we can always find a candidate trajectory that satisfies the constraint. In other words, as long as we don't make some choices that are irredeemable. Once we move here, we cannot find that feasible trajectory anymore. So we have to guard against that eventuality through assumptions or modifications in the structure of the algorithm. So this is the constrained rollout algorithm. And I'm going to illustrate now with the traveling salesman problem. Oh, I'm sorry. I have one more. And then and let me ask for questions. Are there any questions?
I have a question.
Yeah.
What if the trajectory generated by the base heuristic itself violates the constraint tk? What do you do then?
The first one, T0, you mean?
Yes.
T0. It's an assumption that that the base heuristic starts from, generates a feasible trajectory from the initial condition, okay? We have to make some assumptions because everything else is pretty general here.
Cool.
Are there any other questions? Okay, so this is the basic idea, and now we're going to formulate the problem precisely. We consider a deterministic optimal control problem with this system equation, and we define a complete trajectory to be a sequence that goes from 0 to the initial state to the final state, and we have a cost function that's very general. It depends in an arbitrary way on this trajectory. And we also have a constraint that the trajectory is one out of a given constrained set of trajectories. So this is as general as it gets at this point. Now, the problem is that with constraints, coupling stages like that in an arbitrary way, and cost also coupling stages, we can't rely on going state by state because we may have made in the beginning some choices that may affect choices far into the future. So we turn to the idea of state augmentation, and we redefine the state to be at time k the partial trajectory, everything that we have chosen so far. And now this partial trajectory evolves according to a dynamic system, like so. The new partial trajectory is obtained from the old one by adding u, k, and by that. Somebody say something? Okay, I guess somebody should get himself or herself muted. Okay, so the new trajectory, partial trajectory, time k plus 1 is obtained from the old by adding the control and by adding the new state. And now the problem becomes to minimize the final state of this system subject to a final state constraint. So in this way, we don't have this, this coupling across stages where the cost function involves previous states. It only depends on the final state, and the same thing for the control. So this is one trick that we use in order to redefine the rollout algorithm to deal with these couplings across stages. And here is the algorithm. We start at the initial state, and we keep adding controls and states up to the point where we get to x tilde k, the kth stage. Then we have generated this partial trajectory, this y tilde of k. And now we extend this partial trajectory by one control and one state. We extend y tilde k to obtain all these partial trajectories that start from here and end up at these points here. Okay, we add uk and the corresponding next state, and we do this for all feasible controls. And now we run the base heuristic from each one of those. Now the base heuristic generates a partial trajectory, r of yk plus 1. Okay, this one here, and so on. And now we join this part with this part, and we do it for every uk. We join the partial trajectories yk plus 1 and ryk plus 1 for all the different values of uk, and we obtain complete trajectories of this kind. Okay, so we have now these candidate trajectories. Some of them are feasible, some of them are not feasible. So we calculate the set of controls for which this trajectory here is feasible, satisfies the constraint of the problem. And out of those thinned out set of partial trajectories, we find the one that is best, the one that gives you the minimum value of cost. But we minimize not over all controls, but only over the controls for which I get feasibility through application of the base heuristic. Are there any questions here?
Yes, Professor, I had a question for you. In the past, we had talked about problems where we augmented state to take into account time delays. Is this essentially equivalent to those running rollout from those kind of augmented problems?
Yeah, it's the same idea. Not exactly the same, but it's the same idea. Augment the state in order to take into account couplings with previous states. It's the same idea. Okay, so let me now demonstrate the algorithm using the traveling salesman example. This is the same one that we had at the first slide. We want to minimize find the tour that minimizes the travel cost, okay, given by this matrix, but also meets the safety constraint, and two of those tours do not meet it, okay? So we have the cost function, we have the constraints, and we also have a base heuristic. And this base heuristic, of course, the base heuristic can be anything. And I've drawn here with blue. So at state x0, the base heuristic generates a complete trajectory. And it's this one here, okay? However, the base heuristic, when it is at this partial tour, is not sequentially consistent. And instead of generating this trajectory, it generates this trajectory, okay? Now, I did this because I wanted to make the example have more variety. I'm free to do that because, like I said, the base heuristic can be anything. Also, the base heuristic from this partial tour is this blue here, okay? It's this heuristic from AB. It's heuristic from AC, the heuristic from A, and the heuristic from AD is this one. How about the other tours? Well, the heuristic from ABC, it's this one, right? Because there's no choice. Similarly, the heuristic from ABD is this one. There's no other choice, and so on. So I have indicated here the heuristics from A, AB, AC, and AD, and not from the other partial tours because there's no choice. It's implied what the base heuristic is. Okay, so we're going to go through constrained rollout step by step now. This is basically the algorithm of the previous slide. And we start at the initial state, and we will do rollout at A. How will this be done? We consider the partial tours A, B, AC, and AD. We consider this partial tour, and this partial tour. And then we run the heuristic from each one. From this one, the heuristic gives me this. That's a candidate, okay? From here, the heuristic is this one. And from this one, the heuristic is this one. Now, this one happens to be infeasible, so we just throw it away. And we compare this tour and that tour. And the one that wins is this one. So we move from A to AB. That's what this bullet says. We start at A, consider the three possible choices, and we obtain, by using the base heuristic, we obtain these tours here, A, B, C, D, A, A, C, B, D, A, and A, D, C, B, A. Discard this one as being infeasible. Compare this one and this one, and find this one here to be better, and we select AB. So we're now done with the first step of rollout. Is this clear? Is there some question? Okay. So we have made this rollout choice, and now we move to AB, and we do rollout from here again. So what do? We consider this possibility and that possibility and run the base heuristic from each one. Okay? Now, this trajectory here is infeasible because it violates this constraint here. So we throw this one away and we select this one. In other words, we move to ABC. That's what this bullet says. We consider the partial tours ABC and ABD, run the base heuristic to obtain the complete tours ABCDA and ABDCA, and we discard this one as being infeasible, and we select the complete tour, this complete tour. Of course, to be entirely formal, and we have to go from here to here, but there's only one choice, so I'm not showing the completion of rollout. This is the rollout choice at AB, this is the rollout choice at ABC, this is the rollout choice at ABCD. And we have reached the terminal state, and we have the rollout trajectory. Okay, Is this clear? If we did not have this constraint and we did not have this, the violation from these two tours, the rollout would choose this trajectory, which would be the optimal unconstrained trajectory. However, because of the constraint, this was recognized at this point here, and we went the other way. Okay, so now let's go back to theory. What are the properties of this constrained rollout algorithm? Well, obviously, we will need notions of sequential consistency, sequential improvement, and so on in order to be able to assert anything. So there are extensions of the definitions of sequential consistency. Sequential consistency is the same as the sequential consistency of the unconstrained version. Now, sequential improvement is a little different. As part of the definition, we require that the set of feasible controls, the ones from which the candidate trajectories do satisfy the constraint, we assume for sequential improvement that the set of feasible controls is non-empty. In other words, at this step here, there's at least one out of those trajectories that satisfies the constraint. So that's the sequential improvement condition. First, that the set of feasible controls is non-empty. There's at least one that is feasible. And moreover, out of those that are feasible, the Q factor of at least one, the minimum Q factor over those, is no larger than the heuristic cost from here. Okay. Now your notes have this. Your notes have the details of this, but I'm just summarizing this here. In other words, it's the same kind of definition for sequential improvement as before, except that this property here of minimum heuristic Q factor is no larger than heuristic cost at y tilde is satisfied with a minimum taken over the ones that are feasible. In other words, we just discard the infeasible trajectories and we define sequential improvement in a natural way. Now, a lot of things can go wrong if the sequential improvement condition is not satisfied. In particular, there may be no feasible trajectory. You went merrily along here, but all of a sudden you've realized that you reached the point where you can't satisfy the constraint anymore. So to deal with this, there's a fortified version, whereby once you find a feasible trajectory, you keep it for later, just in case you can't find another one that's feasible. Moreover, you replace it with a new trajectory once you find one that's better in terms of cost. So for the case where sequential improvement is not guaranteed to hold, it's not known to hold, we use this fortified version, which maintains a tentative best trajectory and follows it up to generating a better trajectory through rollout. And now we restore the cost improvement property, assuming that the base heuristic generates a feasible trajectory starting from the initial condition. In other words, if our initial trajectory is feasible, then with this fortification, we're guaranteed to always follow a feasible trajectory and one that has no worse cost. The details of this are a little tedious, but they're natural, and you can guess them already by just looking at this bullet if you think a little bit about it. Okay, so there's a multi-agent version also, which I'm not going to go into the details. The multi-agent version applies for the case where each control has multiple components, okay? and therefore the search space is very large. So what we do in this case, we play this trick of reformulating the problem with the control space unfolded, so that the components are chosen one at a time. And then we apply constrained rollout on this equivalent reformulation. So this extension is natural, is simple to deal with. We simply, each one of these decisions is broken up into M decisions, where M is the number of agents, and then we go one step at a time with the base heuristic and all this procedure here that I described. Okay, so now let me return to the traveling salesman problem. This picture is exactly the same as the one that you saw in the previous slide. There's a cost function associated with the travel costs. There's a safety constraint, or a constraint that for the trajectories. There's a base heuristic, which from each partial tour completes the partial tour. Let's look at the issues of sequential consistency and sequential improvement. Okay, is the heuristic sequentially consistent at A? It's not, and why is that? Somebody? Why is it that this heuristic is not sequentially consistent at A? At A, it generates this trajectory. Once it goes through the first step, it generates a different trajectory. Well, that violates sequential consistency. Is the heuristic sequentially improving? Well, we have to check two things. Whether from every one of the partial tours, it can find a feasible candidate trajectory. And indeed, this is so. At AB, it can find this trajectory. At A, it can find this trajectory. At AC, it can find this trajectory and that trajectory also. And at AD, it can find this trajectory, but not this one. This one doesn't qualify. So the feasibility requirement for sequential improvement is satisfied. But there's another requirement for sequential improvement, namely that if you run the base heuristic from any given partial tour, if you run the base heuristic from some partial tour, it's this one here, and there is a neighbor such that running the base heuristic from that neighbor gives you a better or equal value. And it turns out that this is true for A, and it's true for A, B, C, and A, B, C, and AD trivially. Why? Because this tour here has a cost of 27, whereas the base heuristic has a cost of 28. So the sequential improvement condition is satisfied at A, and it's also satisfied at the other nodes fairly trivially because of the simple structure of the graph here. So we have sequential improvement, and indeed the rollout constructs this trajectory with cost 27, which is better than the cost of 28 that the base heuristic constructs from the beginning. However, if we were to change this one travel cost and from 20 make it to 25, then the sequential improvement condition at A would be violated. Why? Because when I compare this with that, I find that I compare this with that one, I find that this one is worse than that. This one is also worse than that. Okay, look at the numbers here. And also this one is worse than that. This one has cost 45, whereas this one has cost 28. So if I were to change this one number, then the sequential improvement condition would be lost. And in that case, you would have to resort to the fortified algorithm, which whenever generates a new trajectory, it compares it to the best tentative that you have, which in this particular case is the initial trajectory. And if you apply fortification to this example, you'll see that the rollout algorithm at A tries to find a better trajectory, but it cannot. The reason is that this one is worse, and this one is worse, and this one is worse, or infeasible in this particular case. So it sticks with the heuristic trajectory, with the trajectory that was generated at A, and rejects this one. So that goes back to the question that was asked by one of you. I'm not sure who was that. What happens if what happens if the heuristic is not feasible from the initial state? Well, you have to assume that, and you have to assume that to prove anything. And if that is not, if that is assumed, then by fortification, you're guaranteed to get a better or no worse trajectory than the one that the heuristic generates from the initial state. Now, okay, there's one more thing. How do I find a base heuristic that generates a feasible trajectory from the beginning? Sometimes this is very hard, but we just skip this question and we just assume that you have a base, that we have a base heuristic that at least from the initial state, it can generate a feasible solution. That's part of the assumption for this problem. Are there any questions here? I went slowly here, and also in terms of pictures, to give you the opportunity to follow all the steps. I didn't see any reaction from you, so that can mean one of two things. Either you got very bored with the details and tuned out, or the slides are so complicated that that you lost track of what's going on. But anyway, since there are no other questions, I'm going to go forward and summarize where we are. Okay, a constrained problem, constrained deterministic problem, and the rollout algorithm for it involves some ingredients, all of which are quite general. Okay, some of you are saying that it's very clear. Thank you for the details. So I'm glad to hear that. Okay, so what are the structural components of the framework that we have developed so far? First of all, we have trajectories, which are defined by a graph, a layered graph showing the transitions from states in one stage to states in a next stage through the use of controls. So this there is this optimal control graph that we're using, and the assumptions here are that the problem is deterministic and is also finite state and control. We will not be able to go through all this argumentation that of the previous slides if we had an infinite control space. We have a finite control space and a finite state space. And we have a graph that defines the transitions. So this is the dynamic system defined by the graph. And we have a cost function that can rank trajectories, either numerically or possibly through the use of an expert. We may have an expert that we ask, given this trajectory and that trajectory, which one is better? And the expert has some kind of way of rank trajectories. So we have a cost, but we'll just assume that we have a cost function, a very general cost function. We have a very general set of constraints, which you can check. We assume that you can check it and determine feasibility of the trajectories. And we have also a base heuristic that starts from a partial trajectory and completes it, generates the remainder to form a complete trajectory. So these are the ingredients of our framework. The problem structure, the dynamic system rather, the cost function, the constraints, and the base heuristic. And now, once I give you the dynamic system, I give you number one, then the other choices are independent of each other. I can choose anything I want, and this does not have to depend on that. This does not have to depend on the other two. Moreover, given 1, 2, and 3, which is the problem, you can try several different base heuristics, or you can combine the heuristics into a super heuristic, whereby which naturally chooses the one that has minimum cost out of the ones that are feasible. Okay, some of the base heuristics for a given from a given partial tour, a given partial trajectory, may not be feasible. So you discard those and use and check and compare the ones that give you feasible trajectories, and then pick the one that gives you best cost. So you can have multiple heuristics, combine them together, and all of these choices are independent of each other. So given a particular type of problem, there are a lot of different problems that correspond to it, and also a lot of different base heuristics, and therefore rollout algorithms that can be used. So that's the constrained rollout algorithm in structure. And now I'm going to look at a particular type of problem involving discrete optimization. So here's the problem. It is very general and very useful. An awful lot of optimization just has this structure here. The problem is to minimize a general cost function, g sub u, subject to u lying within some constraint set. And the only thing that we assume here, other than finite control space, finite choices for u, the only thing that we assume is this component structure. U has multiple components that we arrange from 0 to n minus 1 in the way of stages. So the problem is laid out, the problem structure is laid out like so. We have seen this graph before. There's an artificial initial state. We choose the first control, and the states of the first stage are these. Stage 2, they are these pairs. Stage 3, triplets, and so on. The last stage marks the completion of a solution. These are all partial solutions. This is a complete solution. And it has a cost g sub u, okay? This cost enters here. Now, if we didn't have these constraints, then we could, this would be a shortest path problem, okay? If we had costs only on the arcs, this would be a shortest path problem. But now we have constraints, and some of these trajectories are feasible and some of them are not. So we have to pick our way out from the beginning to the end while maintaining feasibility. Okay, so that's the problem. And we can view it as a special case of a constrained deterministic optimal control problem where the states are not really significant. And they're just artificial, just a single state at every step and only controls. And a single state which is equal to some artificial x0. So for problems where states do not have some kind of intuitive meaning, we may prefer to sort of abstract them out of the problem and use this type of formulation. On the other hand, the range of problems of this is just enormous. Any kind of combinatorial optimization problem that you can think of, matching, routing, assignment, scheduling, bin packing, any kind of problem, including the very difficult ones that are NP-complete and so on, fits this framework. As long as you have this component structure, and you usually do, okay? Furthermore, any integer programming problem can be put into this framework. In integer programming, we have some variables which are these u's really, and they can take a value that's integer, usually 0 or 1. So in an integer programming, in a 0-1 integer programming problem, the solution is a sequence of zeros and ones. And I'm going to give an example shortly. Now, because this problem is a special case of the one we had before, not really a very narrow special case. Actually, this problem is equivalent to the deterministic optimal control problem that we had before. But we can view it as a special case in the sense that there's only one state. Because this problem is a special case, we can apply the rollout algorithm that we saw up to now. And this is the way to provide an entry point for reinforcement learning into the solution of discrete optimization problems. What we're doing here is allowing the use of methods of approximation in value space, approximation in policy space, dynamic programming. We allow these methods to come into this broad range of problems. And now, as I said, this is a very, very broad class of problems, and there are many, many methods for solving them. For example, random search is one such methodology, where you start from some initial feasible solution, and you generate at random a collection of other neighboring feasible solutions, and you move to one that looks promising, and then you search at random within a neighborhood of the place where you are, and you find another solution that's promising, and so on. And of course, you can do this in many different ways, and intelligent ways in particular. But in random search, you go from a complete solution to a complete solution, and then to another complete solution. You don't go from a partial solution to a less partial solution up to a complete solution, which is what we do in rollout. So random search and rollout are quite different in their structure. And this is true also for other methods, local search methods. In local search is like random search, moving from one solution to a neighboring solution and to another neighboring solution within some neighborhood. And the method is defined by the neighborhood and by which you move, which candidate within the neighborhood you select. Again, these local search methods have this complete solution structure. You go from a complete solution to another complete solution and so on. You don't build up the solution component by component. Genetic algorithms are another popular class of combinatorial discrete optimization methods. And again, they have the same kind of property as random search and local search. You operate on a sequence of complete solutions, and you go from one solution to another solution by generating some candidate successors through mutation, extension. There are various operations that you can apply. And okay, if you have some intuition about your problem, you can generate interesting ways to interesting neighborhoods from within which to search. And these algorithms have their successes and also their failures. And they are important classes of algorithms, but the main thing is that rollout is different. Integer programming also has a large variety of a rich methodology. And the part of integer programming that's closest to rollout is branch and bound. I don't know if you've heard this method. I'm not going to describe it here, but it involves fixing integer variables one by one and finding which candidates to fix in some intelligent way using upper and lower bounds and so on. That bears some similarity to what rollout does. So rollout is different. Is different better or worse? I don't know if it's better or worse, but it is good to have different algorithms because these algorithms are flaky and sometimes they don't work. So it's good if your algorithm, your favorite algorithm, does not seem to work, to have some alternatives to try. So now let me go to an example. This is an integer programming problem. It's one of the classical ones. It's called the facility location problem. And I'm going to go slowly. There's a lot of formulas here. So you can ask questions if something seems to be unclear. Okay, so what do we have here? We have some candidate locations in which we want to place facilities, like power plants, if you're talking about electric energy production, or some other kind of facilities, service centers. And there are some candidate locations, and we want to find the most promising locations. So if you place a facility in location K, then UK is equal to 1. If you don't place a facility, then UK is 0. So placement of a facility at a particular location corresponds to a 0, 1 integer variable. Now, these service centers, these facilities, are set up there in order to satisfy some demand, satisfy certain clients. These blue circles are clients that are going to be served at these facilities. And these clients have a certain demand. Client I has demand DI for services. And this demand can be satisfied at a location K at a cost AIK per unit. And a client can actually split his demand between two centers and send a piece here and a piece here. Similarly, in other words, there's infinite divisibility, we assume here, of the demand of a client between the various service centers, the ones that are up, of course, that are operating. Okay, back to facilities. If we place a facility at location K, then we provide capacity CK. CK is the capacity of a facility at location K. And it also has a cost BK. This is cost to set it up, okay? And UK takes the value 0, 1, depending on whether a facility is placed at K or not. So this is the overall constraint structure. And the cost is a linear cost. Okay, this is a bit of a handful. There's a cost for services. This is the service cost. And there's a cost AIK for unit per unit of client I that is served at facility K. So this is a linear cost that depends on the y's. The y's are variables also, okay? Optimization variables in addition to the u's. There is also a linear cost that penalizes the placement of facilities. If you build a facility at location K, you have to pay a cost BK. And if you don't build a facility, UK is equal to 0, so you don't have to pay that cost. So this is a linear cost function in the variables y and in the variables u, except that the u's are not infinitely divisible, and they can take only the value 0 or 1. And what are the constraints here? Well, of course, we have the integer constraints that the u's can only be 0 or 1. And the service allocation and the facility assignments must be such that the total demand is satisfied. In other words, these y's have to be services have to be non-negative. They should add up to the demand of client I. So for every client, the portion that allocates the various facilities should add up to the total demand DI. So we have this constraint, this constraint, this constraint here, and also the constraint that at location K, at facility K, assuming the facility is built at location K, this can only serve demand up to a level CK. In other words, the total demand that's being served at location K should not exist CK if UK is equal to 1, and no demand can be satisfied at location K if there is no facility that we have built at location K. Okay, so this is the classical version of the problem, but we can make it even more difficult. There may be additional constraints on U, but we will ignore for the moment. But let me give you an idea of what these additional constraints can be. Okay, let's go back here. This is the definition of the problem and a transcription into our standard form of minimizing G's of U over U belonging to C. What is C now? The constraint set is the set of all the U's that are in 0 or 1 and also can satisfy the demand and perhaps some other constraints, like some public policy constraints, like zoning constraints.
I'm not sure.
Did I hear someone? Zoning constraints that say that within a certain geographic region, you cannot build any facilities, or you can build only one facility and no more. And so there may be groupings of locations that have special properties that are not shared by locations in other places. This is what we mean by public policy constraints or additional constraints. But let's not worry about those, although our methodology can address those, okay? Which makes it, which adds to its generality. So this is the constraint set of the problem, and this is the cost function of the problem. Now, okay, here's the cost function. I told you that it's this one. However, if you look at this problem and you look at the variables U and the variables Y, you realize that the really important variables are the U variables. If I give you the facility locations, then the remaining problem is a linear programming problem that can be solved very quickly. It's what's called a linear transportation problem, okay? It's a classical network flow problem that is can be solved in polynomial time by very efficient algorithms. So if the placement variables are known, the remaining problem is easily solvable. So we are going to formulate our problem in terms of the difficult variables, and the others, the y's, are going to be determined automatically through this optimization, where H is the set of all feasible demand allocations, the ones that are non-negative, and satisfy the constraints. So once I fix the U's, the constraint set of this problem is determined, and this problem becomes a linear programming problem, and its optimal value, I'm going to call it G's of U. In other words, I have eliminated the variables y from the problem by saying, well, they're automatically determined once you determine this location variables u. Okay, so now I have the problem in the way I want it. I have a cost function involving a sequence of decisions, and I have a constraint set, and I can check whether for a given sequence of decisions this constraint is satisfied. And now I'm going to apply a rollout whereby I will first pick the variable of the first location. Do I build or do I not build at this location 0? Then I go to location 1. Do I build or not build? And so on, go all the way up to the last one while applying some kind of base heuristic and checking also for constraint satisfaction. So are there any questions?
Is this an example of a problem where certainty equivalence has been applied? Because I would assume that the DIs in general are random variables, but in this case, we're just treating it as some known constant, right?
Okay, this is a deterministic problem. Now, how you have arrived at this problem, we don't examine here. It may have been the result of certainty equivalence. In other words, there may have been some random variables here. For example, this demands, DI, okay? They are random, and they probably are changing over the calendar year. But we assume here that they have been replaced by deterministic quantities. So we're using, in a practical sense, we are using certainty equivalence. However, from a mathematical point of view, we assume that these are known. They're not random. Does that answer the question?
Okay, yep, thank you.
Okay. Okay, so now we are going to apply this constrained rollout algorithm, considering places one location at a time. That means we first fix U0, then U1, and so on. So at stage K, we make the placement decision UK from 0 to 1 at this location, and there are n altogether stages. And here's our base heuristic. I could use any of a number of base heuristics, but here's the one that I'm going to be using here. The base heuristic completes a partial trajectory, right? So given a partial trajectory, it must have a way of completing this trajectory with additional U variables. And it chooses to place a facility in all the remaining locations. In other words, having fixed U0 up to UK, there are two candidate trajectories to consider. One is where we set the next facility to 1 and all the remaining facilities to 1, according to this base heuristic. And the other candidate trajectory is not to place a facility at the next location, but that place a facility in all the other remaining locations are as per our base heuristic. And now, at U0 up to UK, we have two candidate trajectories, and we check for feasibility. And this one is going to be feasible. Why? Because it builds up everything, okay? If we have reached up to here with a state feasible so far, we're going to remain feasible because the base heuristic is very generous and allows us to build a facility in every location. On the other hand, this one may not be a feasible trajectory because this indicates that we do not place a facility in this location, and this location may be a critical one. This particular, and without building it, then we can't satisfy the demand. Okay, so we looked at these two, and depending on which one yields feasibility and minimum cost, we move to UK plus 1. It may be 0 or it may be 1. And now we note that because of the nature of this base heuristic, sequential improvement is satisfied. The reason is that, feasibility is satisfied because of the particular choice of the base heuristic, and also, it's easy to see that the minimum Q factor between these two has to be less than the Q factor of the cost of the base heuristic starting from this location. Basically, the base heuristic here is not only sequentially improving, but given feasibility is also sequentially consistent. In other words, it stays the course. You start out with a base heuristic that sets all to 1, and then as you move forward, it continues. The tail of the trajectory generated by the base heuristic also consists of 1s. So it's easy to start to verify that sequential consistency is satisfied and also feasibility is satisfied. So you get cost improvement over the initial choice, which would be to build everything, build a facility in every location. That's what the original, what the base heuristic would give you starting from the initial state. So trivially, you get cost improvement, and generally this algorithm, in my opinion, works pretty well, particularly since it can handle some very, very difficult constraints, which would not be possible to handle with other methods, like integer programming type of methods. Okay, are there any questions now on this example?
I have a question. So setting dynamic programming aside for a second, if I'm just looking at this problem as an integer or linear program, I would be finding, like the total number of variables I would be finding values for would be all of the U1 through UK, or all of the UK values, but also all of the Y sub IK values, right? Like, yeah. Okay, so this cost function has two parts. It has trying to minimize the demand and also trying to minimize the number of facility locations that you're going to put down in total. So you said that, so we have our control space corresponding to only putting down facilities or not. And then you said once you have a facility assignment, then at that point you feed the rest of it into a linear program to figure out what is the best way to allocate the demand, right?
Yeah.
Okay, and so we've seen before that, like for example, in the case of the linear quadratic case, that sometimes your controls can be continuous as well. So I guess my question is there any way to adapt this framework to just purely solve a linear program, where, for example, if your controls were in some continuous range 0 to 1? Because I know we've seen that before.
The answer is that would lead you to a different kind of methodology. Branch and bound, some major methodology in integer programming, as I as I mentioned, does this. In other words, branch and bound at any one state allows, at any one point, has variables that are fixed to integer values, and also variables that are free to take values in the range from 0 to 1.
Okay.
So there is this feature of relaxing the integer constraints and solving corresponding linear programming problems in branch and bound. In rollout, that's not done.
Okay.
We treat the variables as 0 or 1, and the remaining variables are automatically determined by solving this linear transportation problem, minimizing this objective here, subject to these constraints.
Okay.
So we always operate with integer variables. And that's the difference. That's an important difference between this methodology and the branch and bound integer programming methodology.
Because if, for example, if your y variables were restricted to be integers, maybe not 0 or 1, but 0 through 10 integers, they could also be a part of your control space, couldn't they?
They could, yeah. It's all a question of whether you can solve this problem here easily or not. Mm-hmm. If the y's are not restricted to be integer, then this problem is very simple to solve, relatively speaking.
Right.
However, if there are additional difficult constraints on the y, which make this problem non-polynomial and hard, then you're faced with a different type of animal, and you have to treat it differently. And you have perhaps to consider simultaneously the choices of uk and yik. But because here this problem is simple, relatively speaking, you can follow the solution methodology that we have discussed. There's something else about these transportation problems. They tend to have integer solutions under some conditions. So even though we have assumed here that the y's are fractional, could be fractional, in reality, if all the other data of the problem is integer, then these transportation problems also have integer solutions. Okay, that takes us into different territories, and I'm not going to go any further.
Okay.
But there's one thing that I want to mention, and it's the last bullet here. There are a lot of transportation problems here, right? For every new value of u, 0 or 1, you have to solve a transportation problem. And on the other hand, these transportation problems are similar. They have similar data, and then you can use the solution of one transportation problem to hot start the solution of the next transportation problem. And there are algorithms in network flow theory, network optimization, this auction algorithm in particular, that are very well suited to hot starts, starting the solution from an already good solution. And these auction algorithms are very suitable for as intermediate solution methods for obtaining the values, the cost values.
Okay, thank you.
Okay, guys, so we'll keep on going. And now we're going to go into Minimax Control. We have been minimizing either deterministic cost functions or expected values involving probability distributions. Now, in Minimax Control, there are no probability distributions. Instead, the disturbances are chosen by an adversary who is also very smart and can see what we are doing. So in Minimax Control, we guard against the worst possible decisions of some adversary. And okay, so we'll take a break first, but let's take a working break. I hope you like my picture. It's meant to impress on you the nature of worst case. So what I'd like you to do, we'll take a 15-minute break, and what I'd like you to do is think about how you would formulate this adversarial type of problem, where the disturbances do not have a probabilistic description, but instead they have a set membership description. They're just known to belong to given sets, which you know. And then we have an adversary that chooses this malevolently. It's adversarial and also omniscient, knows what you're going to do. So no matter what I do, this guy, I have to assume that he knows what I'm doing and will choose the best possible, the worst possible decision for me, the best possible decision for himself. Now, all of this can be implemented, can be thought in the framework of dynamic programming. And there's a principle of optimality, a minimax version of the principle of optimality. And as you take a break and you're having some coffee or tea, you may think about this, and we will come back in exactly 15 minutes, which would be 6 o'clock Arizona time, okay? Okay, so I'm going to mute myself. We're going to spend the remainder of this lecture on Minimax Control. And like I said, there is a different description of the uncertainty. And do you have any thoughts as to how we would deal with that? Okay, let me just say that the change from a probabilistic description to a set membership description is going to manifest itself in, instead of minimizing an expectation of the present plus the future, we minimize the maximum, the worst that can happen for the combination of present and future, assuming that we act optimally in the future. And the reason a principle of optimality holds, you can view it as a principle of optimality, is because it's a manifestation of a property that's preserved, a Markov property, namely that if you know the present, you don't have to know the past, how you got to this present. All you have to know, all you have to deal with is the future, and the future can be broken down into the first stage and the remaining stages, assuming we act optimally. This is all at a heuristic and intuitive level, but can also be verified by mathematics that are very similar to the ones that we use for probabilistic descriptions and expected values and stochastic optimal control. So, okay, about the name, first of all. The name that I'm going to be using is Minimax Control. And for a while, it was known, it was the dominant name for this type of problem. Nowadays, you see the name Robust Control, which is about the same thing. Robust optimization. It deals not only with control, but also with other optimization problems, like the combinatorial optimization problems that we have been discussing, or linear programming type of problems. The original name was Games Against Nature, okay? It was used in the late 40s and 50s. And that was the period when game theory was very prominent. It was sort of the queen of the sciences, or the applied mathematical sciences. And And so people tended to describe theories in terms of games. However, as this picture suggests, I don't think it's wise to play games against nature, be it in Indonesia with tsunamis, or be it in New Orleans with flooding, or Texas with rolling blackouts. So it's not a game, but we certainly need to guard against the worst case in many settings. So let's go into the mathematical description. And I'm going to talk about finite horizon problems. The infinite horizon problems are very similar. Along the same lines to finite horizon stochastic control versus infinite horizon stochastic control. So in terms of problem formulation, everything is the same. You have a system perturbed by disturbances, and you also have a cost function over n steps. And you assume that the disturbances at time k are going to be chosen from some set that may depend on the current state and control. This local dependence allows the development of dynamic programming algorithm. So the Minimax control problem is to find a policy. We're dealing still with policies, functions of the current state that satisfy certain constraints, that for all xk and k, that are satisfied for all xk and k, and minimize this cost function. Okay, so what is this cost function? We have the policy. This is a number here that corresponds to using that policy at stage k and the disturbance being wk, as before. So this whole thing is a number, and for the given policy, at a given initial state, we consider the maximum, the worst possible value of this number, maximized by optimal choices of the w's from within the constraint sets that they're supposed to lie. So rather than try to parse the details of this notation here, just see that wherever you had expected value in stochastic control, you now have maximization. Instead of expected value over with respect to probability distributions that depend on current state and control, you have maximization over sets that depend on state and control. And using a similar rationale as for the stochastic case, we have a dynamic programming algorithm that uses, again, maximization in place of expected value. The optimal cost of the tail problem that starts at xk involves minimization over the first stage cost and the cost of the remaining stages, assuming that the disturbance acts malevolently as bad as possible, and assuming also that we're going to be minimizing in the future. So this is very similar dynamic programming algorithm. It has the same difficulties, namely lots of computation to find these J stars, lots of memory to store the optimal policy and the J stars, and it has some additional difficulties. The expected value operator here is linear. In other words, expected value of a sum of two numbers is equal to the weighted, is equal to the expected value of the sum of the expected values. Has a linearity property. It's a linear weighted sum weighted by the probabilities of the distribution. Now the maximum operation is not linear, it's non-linear. That's one thing. And another thing is that whereas you could compute expected values by using Monte Carlo simulation, this is not possible with maximization. You have to solve an optimization problem. For each u, to calculate this q factor, you have to solve a maximization problem, which is generally more difficult than computing an expected value by simulation. And now this is the kind of thing that affects rollout and also policy iteration, because they involve they involve before expected value operations. Now they're going to involve maximization operations. So it will be possible to define a rollout algorithm and define also policy iteration in the context of an infinite horizon, but executing it has to be done without Monte Carlo simulation. Now, once we have this dynamic programming algorithm, and of course we recognized calculating these J stars is very difficult, we are led to the idea of approximation in value space. And with one step look ahead, it looks like this. It applies at state xk the control that minimizes this expression here, which involves a maximization and also an approximation of J star by J tilde. So this is like the optimal policy generation, except that we use J tilde with J star. And we can view this as being offline training. And we can view this as online play, calculating optimal controls, suboptimal controls online by using J tilde approximations. And this is one step look ahead. It's also possible to do approximation in value space with multi-step look ahead. And let me get to that. Are there any questions about the slide?
So it seems like the principle of optimality suggested here would require us to be able to swap the order of minimization over the future controls with the maximization over WK. I guess I'm just wondering, is that possible in general?
Okay, this minimization involves this minimization here involves the definition of JK star involves minimization over UK and UK plus 1 and all the remaining controls, and maximization involves maximization over the future WKs. The min-max can be taken inside the bracket. I think that's what you're referring to. Can be taken inside, and that's how this J star here comes in. And the reason is that the cost is separable in the components, and one component for each stage, and also the constraints are not coupled over stages. And that's how you take the min-max inside. That's how you prove actually the validity of this algorithm. Does this answer your question?
Yes, thanks.
Okay, so now let's go to approximation value space with multi-step look ahead. We have some J tildes, and at state xk, we do an optimization involving the first L steps, L step look ahead. So this is the L stages cost that depends on UK and also the control functions for the remaining stages. Involves also the WKs, and we maximize this expression, and then we minimize over this L step policy. So instead of addressing an n-step horizon problem, which is the original problem, we truncate the horizon to just L steps and use a future cost approximation with this J tilde. Now, in general, any J tilde function is permissible, including ones that are obtained by forms of offline training. Okay, you may find some data. You may get some data from which to construct this approximation using a neural network, for example, or you may solve a related problem. Anything that we have learned about constructing J tilde functions for the stochastic case applies also to the minimax case. Moreover, in these pictures, there are potentially approximations in 3 places. The 3 approximations. Approximate this minimization by a simpler one, like a multi-agent one, for example. Approximate this maximization by something else, and approximate this J tilde. Now, these 3 approximations can be designed independently of each other, and that's the nice thing about them. Like in the stochastic case, here also we can mix and match schemes for these 3 minimizations, these 3 approximations. How about this L-step minimax problem? It can be solved by dynamic programming, because dynamic programming can solve any finite horizon problem. So it can solve this L-step problem. And of course, this can be not so easy, but if I start at a given state and the number of possible controls per stage is relatively small, the number of possible W's is also small, then the look-ahead tree for this minimax control problem does not grow so fast, and we may be able to go a number of steps forward. It may be feasible to have a relatively small look-ahead. It's always a problem to decide how many steps of look-ahead we should use. Now, there's an interesting technique for solving this min-max control problem called alpha-beta pruning. Some of you may have seen it in algorithms courses. It's used to simplify minimax search over a finite number of steps. It's basically a technique that allows you to decide that it is not necessary to search forward from a particular point, because that would not change the outcome of the solution. It would not change the solution. This is used in games like chess extensively, but I'm not going to go into that. And by the way, this is not an approximation technique. Alpha-beta pruning is exact. In other words, the solution of the problem with or without alpha-beta pruning is not going to change. There are variations of this look-ahead process using selective step look-ahead. So for some controls, you may use a relatively shallow search, and for other controls that are presumably more interesting, you may use a longer search. And generally speaking, this is the type of algorithm that people use in non-stochastic games, min-max type of games like chess. And this is the algorithm that most chess programs use for online play. They may do offline training to obtain this, but for online play, they use this type of algorithm. And so there's a lot of experience with this type of approximation in value space, particularly in the context of games. Okay. Now, rollout is a particular way of choosing this J tilde that uses a base policy. So let me go into that. And I'm going to talk about one-step rollout, okay? For minimax in discrete spaces problems, so that all the minimization, the maximization here can be done over a finite space. So what does rollout do? At a given state, it forms a Q factor for every one of its feasible controls. Now, this Q factor is not what you have seen before. It involves maximization instead of expected value, but it involves the same first stage cost, and then a cost approximation that involves using UK to go to the next state, using the base policy. The base policy is just a sequence of functions of the current state. And it involves also the W's that are going to occur between K and the end. So all of this expression here can be viewed as something as what the maximizer optimizes over, and it may be viewed as a Q factor of control UK. So that's what this bullet says. At state xk, for every possible control, we compute a Q factor by this expression here, and then we choose the control that gives you minimum Q factor. On the other hand, this problem is not an expected value calculation, which you can do by simulation. Instead, it is an optimal control problem with the control variables being the W's now. And it's a maximization problem. It is not a shortest path problem. It is instead a longest path problem, assuming everything here lives in a finite space. So there's some kind of a look-ahead tree, and the W's are obtained by weeding through the tree, our route, to find the longest path, not the shortest path, the longest path. Now, some of you may have heard that longest paths are nasty, where shortest paths are nice. Longest path problems are nasty, but not for acyclic graphs. If you have an acyclic graph, you can convert a longest path problem into a shortest path problem by simply changing the sign of the lengths of the arcs. So this longest path problem is like a shortest path problem, except that, okay, it's done for maximization over an k minus n step graph. So we have Q factors obtained by longest path problem solutions, and we have the rollout control computed like so. And any policy can be used as base policy, but it has to be a legitimate policy. It has to consist of a sequence of functions of the state, not a heuristic like in deterministic problems. We make this distinction between the rollout for deterministic problems and the rollout for stochastic problems. For deterministic problems, we can choose a heuristic that doesn't necessarily have to be sequentially consistent, doesn't have to correspond to a policy. It can be something more general than that. But here, the base policy must be a legitimate policy, and the natural form of sequential consistency holds, assuming that, okay, we don't use a terminal cost approximation, we don't use a truncated rollout. And sequential consistency implies cost improvement in the usual way that we are accustomed in for Minimax for rollout algorithms. The same kind of proof goes through for the Minimax case as well. And there are similar variations. Truncated rollout with terminal cost approximation. Additional constraints, like in constrained rollout. But once you introduce this, there's no cost improvement guarantee. So in principle, Minimax rollout is similar to rollout for stochastic problems, and however, there's not much experience that is available with this kind of Minimax rollout. If someone has an interesting problem to do for a term project, that would be welcome, because I really don't think that there have been many implementations or any implementations of Minimax rollout. Okay. Let me say a few things about trajectory constraints, okay? Like in constrained rollout for deterministic problems that I talked about earlier. Okay. Here we have to consider partial trajectories because the constraint may be coupling the previous applied controls and the future applied controls. So for a given partial trajectory, we calculate the corresponding Q factor as earlier. However, the longest path problem that you solve here may violate feasibility, this constraint. Remember, we're dealing with a malevolent opponent, and the malevolent opponent will do everything possible to get us off feasibility. So we calculate the Q factor for every control in a restricted set of controls that depend on the partial trajectory so far, because the constraint may depend on the previous values of states and controls. And these are the set of controls that guarantee feasibility. No matter what the malevolent adversary will do, he cannot get us to violate this constraint if we use the base heuristic. Okay, so this is again a longest path problem. We can solve it and find the minimum Q factor and the control that attains this minimum Q factor. And this is what the rollout algorithm will apply at this partial trajectory. And there's also a fortified version of the algorithm. And the assumption that's needed here, similar to the case of deterministic constrained rollout, is that at the initial state, the base heuristic produces a feasible trajectory, one that's feasible for all possible disturbance sequences. Okay. Once you have that, then you can introduce fortification and guarantee some kind of a cost improvement in feasibility. So in a nutshell, all the ideas that we have discussed so far apply in modified form for these minimax problems, including the constrained version of the rollout algorithm. For stochastic problems, there's no constrained version of the rollout algorithm because of the presence of the disturbances which are stochastic. However, for minimax, you can apply constrained rollout. Are there any questions?
Yes, Professor, I have a question for you. If we have an adversary who's only affecting uncontrollable state components, are we able to form new cost functions just taking the worst case uncontrollable components into account and then plug that into the ordinary DP algorithm?
I'm sorry, I missed the first part of your question. What does the adversary affect, you said?
Oh, just if they're only affecting uncontrollable state components.
Uncontrollable state components.
Yeah.
Yeah, what about that?
I'm just wondering if we can do something similar like we discussed previously. I think when we discussed uncontrollable state components previously, we formed new cost functions by taking a conditional expectation over those uncontrollable state components. I'm wondering, like, can we just, in this case, form the new cost functions, taking the worst case uncontrollable components into account and then plug it back into the ordinary algorithm?
Yeah. Well, I'm glad that you have remembered uncontrollable state components, because this is a little bit mysterious, part of the more mysterious parts of this course. I'm glad you have understood what that means, and you're curious about it. I haven't thought about your question. Okay, I haven't considered it, but I'll think about it. And if you write me an email message, I'll be able to respond. But I doubt it, because the transcription of the dynamic programming algorithm where the uncontrollable state components are taken care of in a more efficient manner, that depends on the linearity of the expectation operation, if I'm not mistaken. And I don't believe that you can have such simplifications in the minimax setting, but I'll have to look into that.
Okay. All right, yeah, thank you.
Okay. So now I have a last slide. Okay, what's the relation of minimax and game theory? Okay, usually people talk about games, zero-sum games, non-zero-sum games, or Nash games. Non-zero-sum games cannot be dealt with by dynamic programming, and except in the case of a team theory problem, where all the cost functions of the agents are the same. However, non-zero-sum games involve two directly opposing adversaries, and they are related to dynamic programming because they are related to minimax problems. So what is a zero-sum game? You have two players and a cost function. One player aims to minimize the cost function, and the other aims to maximize the cost function by choosing their variables. The cost function depends on both players' variables and policies in the context of a dynamic system, a control type of setting. Now, game problems have a very incomplete theory when it comes to reinforcement learning. Game problems are studied extensively. It's a very fundamental discipline. Game theory is a very fundamental discipline. But from the point of view of reinforcement learning, I think it's important to keep in mind that actually a game problem, a zero-sum game problem, splits into two minimax control problems. The first one is the min-max problem, where the minimizer chooses a policy first, and then the maximizer chooses the policy second with knowledge of the minimizer's policy. The max-min problem is like a min-max problem with signs reversed, okay? But we call it max-min, and we have the maximizing player choosing policy first, and then the minimizer player looks at the policy that the maximizer has chosen, and then chooses his own policy afterwards. Now, these two problems are different, okay? And they have different optimal values. And generally, it's easy to see that the max-min optimal value, the optimal value of this problem from some initial state, is less than the min-max value, the optimal value of this problem from the same initial state. This is true for every initial state. And this is very easy to see. It's an elementary fact. However, game theory, zero-sum game theory, is particularly interested in situations where the two values are equal. So in terms of value, it doesn't matter whether the minimizer or the maximizer plays first. And this is not true by any means in general. It is most of the time not true in the context of minimax control. However, game theorists are particularly interested on the conditions that guarantee that this is true. And there is theory about that involving mixed strategies and so on. I don't want to get into that. And this theory extends to dynamic programming. However, when it comes to practical reinforcement learning, you're not going to have this, okay? You can't even think in these terms. You can think in these terms in terms of the theory, as a matter of theoretical interest. On the other hand, from a practical point of view, you're not interested in achieving this equality, nor do the methods of practical reinforcement learning produce equal values, min, max, and max, min, even in settings where it's min, max is equal to max, min without approximations. Once you introduce RL type of approximations, this is gone, okay? Now, there are various interesting questions about game problems and approximations. Okay, how do various algorithms work when approximations are used in the min-max or the max-min problems? So for example, suppose you use approximation in value space, or you use rollout, and you use various types of approximations, base policies, and so on. How will these algorithms work when you have two players? There's one thing that you can say, and that's about the only one that you can say as a practical matter. If you fix the policy of one of the opponents, you can improve the policy of the opponent if you fix the policy of one of the opponents, you can improve the policy of the other opponent by using rollout or policy iteration. Why is that? Because if one of the opponents has a fixed policy, then the problem becomes a one-player problem. It's like the ones that we have been discussing so far. It's no different. Does it pay to consider an opponent with fixed policy? Well, you may have an opponent that you want to prepare for. You know, you have access to how he plays. You have access to his policy, and you can optimize for this policy. So, for example, consider AlphaZero, chess, and suppose that AlphaZero decides to play with the world champion, Magnus Carlsen, the current world champion. Then it could improve its play by asking Carlsen to play with AlphaZero, let's say 10,000 games, pay him a few $1 million, okay, and play 10,000 games and learn from his play to play better. You would get an AlphaZero specialized to Carlsen that would play better than the plain vanilla AlphaZero that would play against you and me. Okay, so that's fairly obvious, but it's an important thing to keep in mind. And that's just about the only thing that you can say about the reinforcement learning algorithms that are being used in game theory, including the ones that have been used in AlphaZero. So in particular, suppose that instead of having a fixed policy for one of the opponents, and then improving the policy of the other opponent, can we improve the policy simultaneously? In other words, is it possible to have to play against Magnus Carlsen, and as you improve the playing policy against him, he changes his policy. Not only do you learn from him, but he also learns from you, okay? Then what happens? What kind of algorithm would you use? And what kind of guarantees does this have? Well, there are practical algorithms that you can use, but there are no guarantees for them, and there is no reliable theory for them. In particular, the kind of algorithm that was used in AlphaZero, which involves training and changing the policy for both the maximizer and the minimizer. In other words, generate new player that's being used by both the maximizer and the minimizer. That's certainly an algorithm that looks good, and in fact has worked spectacularly well, but there's no theory about it. Not theory as an approximation, in terms of approximate dynamic programming, and no theory, and very little theory even if you do exact calculations, which you cannot do, exact policy iteration. But for the type of algorithm that's used in AlphaZero, there's no theory really, because the players are simultaneously changing their policies. One does not stay still while the other one improves. So that's all I can say about the use of reinforcement learning in games. It's not that it's hopeless. In fact, it can be spectacularly successful, as case studies have shown, with both with chess and also with Go and related games. But there is no rigorous theory that covers these algorithms. And so we have limited understanding in that respect. Does this make sense? Are there any questions? Okay, so that's the end of the lecture. We have exhausted the subject of finite horizon rollout. A lot of the insights that we gained are going to become useful later when we talk about approximate policy iteration in an infinite horizon context. However, in the next lecture, we're going to take a break and look at neural network type of architectures, or more generally, parametric approximation architectures, how we use them to construct value and policy networks. And video lecture 6 from the 2019 offering of this course is very adequate for this material. I'm going to use some of this video lecture in my class next week, and I suggest that you take a look at the lecture before coming to class. That will be helpful, because we're going to be skipping a lot of material and we're going to be going fast. After we cover parametric approximation architectures and the issues of training of value and policy networks, then we're going to go into infinite horizon problems, and then we're going to focus on both the theory and also approximations in terms of policy iteration. So this is it for today's class. Are there any questions? Okay, guys, see you next week.